Newton's third law, F1 on 2 is the opposite of F2 on 1. Put a minus sign right there, and we've got the most fundamental statement of all of Newton's laws. Is it more fundamental than number 2? I don't know, but I kind of think maybe. Yeah, I kind of think it is. So here's the thing. I've developed a test of Newton's third law. I have a loop here with another string running off there that won't be important. I just didn't want to cut it. And I have two, well, they're called spring scales, or you could call them force measuring devices. And I'm going to exert a force from one spring scale. And the interesting thing is the other spring scale moves. So that's telling us something interesting is probably happening. I'm going to go over here and not show you that one, but show you this one. If I exert a force of 3 newtons, how much force do you think the other one is exerting? If I have that loop of string and I pull it to the right with a force of 3 newtons, how much do you think the other scale is feeling? All right, so let's set that up. We've got a loop, and here's the free body diagram for the loop, and there's a force to the right of, well, I could call it a force applied, and it's 3 newtons to the right, right? So the question is, if the loop's just sitting there, how much force is on the other spring scale? That's our question. So, what can we do? We can think about the loop, and the loop is in equilibrium, and the loop therefore must have no net force on it. Here's the statement of equilibrium. The net force is mass times acceleration, and we're saying that the acceleration is 0, so the net force then, must be 0. And that means there must be a force the other direction that we propose is equal to, I'm going to call it F app, comma, other, is also 3 newtons, but to the left. Of course, you see that in the picture. And, oh man, that's a little bit short. We should draw it like that. Yeah, those are about the same size. So let's check that out. Here's the loop, and here are the 2 scales, and I see when I get to 3 newtons on the right one, I'm at 3 newtons on the left one. In fact, this is always true. Look at this. 1, 2, 3. I cannot get these to read different values. Now, some of you will say, what if you moved one really fast? And I mean, yeah, I can try that. At some point, the information that this force has been exerted takes some time to get to that force, but in that short time scale, this sucker is accelerating. So we don't have F is ma equals 0 relationship in that case. It's not equilibrium during that time. But for every stable situation, we've got those forces to be equal. I want to actually argue that the force of the loop on the scale is the force of the scale on the loop. And I think that this picture, if you really think about what's happening here, where these both say 3, that proves Newton's third law for you. And it's not just an equilibrium case. At every instant that this scale is pulling the loop is pulling the scale. In fact, that's the only way that I can get this scale to not read 0. If I exert a force on it, then it exerts a force on me. For instance, well, scales are so fundamental. Spring is inside of here, and the spring is teaching us about what's happening. If I exert a force on the spring, then the spring exerts a force on me. And me exerting a force on the spring causes the scale to move, and the scale exerting a force on me causes that little bump in my skin. All right, so that's Newton's third law. It's so important to understand Newton's third law because many people misunderstand it. What's a typical misunderstanding? I'll see if I can think of one. Thought of a typical misunderstanding. While you were gone, I put a stool here, and I'm going to set an orange on that stool. Here you go. And I'm going to make a free body diagram for that orange. Here's the free body diagram for the orange. I chose purple to represent the orange. I put a dot in the middle of the purple orange, and I'm going to draw some forces that are acting on the orange. First of all, we've got mass of the orange times baby g. And we've got another force that's upward on the orange, and that's probably called the normal force. So a lot of people will try to argue for you, and this is a gross misunderstanding, but they'll try to argue to you that those 2 forces are equal because of Newton's third law, which is ridiculous. because I can take an orange and I can cause the upward force on it to be more than m baby g or less than m baby g. If I cause the force on this orange to be more than m baby g, then the orange will accelerate upwards. If I cause the force on the orange to be less than m baby g, then the orange will accelerate downwards. For instance, if I just like karate chop, if I attack this stool, then the orange will accelerate to the flow. So clearly, if I'm saying that this force relationship is always true, then I can't just take out a stool and then violate the fundamental laws of the universe. What I'm getting at here is this is not a Newton's third law relationship. This relationship is a Newton's second law relationship, and the only way that you can say that these two forces are equal is if you observe that the acceleration is zero. If the acceleration is zero, then we can say that the normal force minus mg is equal to zero, and if the normal force minus mg is equal to zero, then the normal force is mg. And that's fine, but it's not always true. It's a beautiful thing, but it's not always true. So I was afraid that what I'd just drawn here might be misleading for you. This seems to imply that these two forces are equal because it's Newton's third law. Those two forces on my loop were equal. Let's just cut the loop out entirely, because the system was in equilibrium. But when I'm thinking about not that, I'm thinking about like one scale acting on another scale, that's the same as this scale acting on this scale. So that's why these two scales have to read the same thing. I cut the loop out of the picture now so that you can believe that these forces are going to be equal all the time, because, wow. Because why? Because these two pieces of metal are linked, and when one moves on one, the other moves on the other. And because these springs are calibrated to the same spring constant, we're going to get the same motion on each side of the scale as a result. So Newton's third law should not ever be confused with Newton's second law. And this is a very important hint to discovering why things can move. Good luck and good night. One final thought. Sometimes, when I'm in a good mood, I try to sneak up on Newton's third law, like, the paper's not touching me, right? It's not touching me, it's not touching me, and I'm not touching it. But I try to, like, get the paper a little bit concerned. What's gonna happen? What's gonna happen? I don't know. Am I gonna touch it? I don't know. But then I go over here, oh, and I touch it. And what I notice is every time I touch it, it touches me. And the way I know it's touched me is I can feel it pushing my finger in a little bit. You might want to try this with your desk or your computer or something. Sometimes I go underneath the table a little bit, and I come over here and I'm like, table, ah! And then it always, I mean, I can never say it beats me, but the table just sort of is ready to exert a force as soon as I'm exerting a force on it, and I can't beat Newton's third law. You try it. You can't do it. Really frustrating. Newton's third law applies to everything in the whole universe.